The National Electrical Code, or NEC, does not always require grounding conductors for stationary motors if the equipment is grounded through the metal raceway or cable tray. In scenarios where motors are mounted on steel structures that are welded together and bonded to the electrical system, particularly through a bar in the slough, metal conduit, and rigid flex, it is often found that the motors are effectively grounded through the equipment grounding conductors or EGC in the conduit. Let's delve into specific grounding options in this context. Firstly, consider the option of eliminating the ground wire from the motor pecker head. This approach is generally acceptable if the existing grounding path meets the NEC requirements for an equipment grounding conductor. However, it is crucial to verify this through formal ground and bond testing to ensure compliance and safety. Secondly, there's the option of running a short green jumper, say 12 to 24 inches, from the motor head to the steel beam mount, which is already bonded to the tower, building, and conveyor system. This option is typically unnecessary. The existing welded connection should already provide an adequate bonding path to the electrical system. Thirdly, one could consider running another ground wire back to the transformer along with the circuit conductors via feeder motor control panels or NCP. This option, while sometimes considered, is not usually required and doesn't provide significant additional benefits in terms of grounding effectiveness in a well-bonded system. It's important to be aware of the Mine Safety and Health Administration, or MSHA, regulations, especially in relevant work environments. MSHA often has specific requirements for grounding and bonding, especially in hazardous areas. Consulting with a qualified electrician familiar with MSHA regulations is highly recommended to ensure full compliance. In general, if the motors are adequately grounded through the metal conduit and the steel structures, adding an additional ground wire from the motor pecker head is not necessary. However, there's a crucial caveat: formal ground and bond testing should always be conducted to verify the integrity of the grounding path. This testing is essential to confirm compliance with both NEC and MSHA requirements, guaranteeing a safe and reliable electrical system. Let's explore in detail the concept of equipment grounding conductors and their role in ensuring safety and compliance. An equipment grounding conductor, or EG, is a critical component of electrical systems designed to provide a low impedance path for fault current back to the source. This low impedance path facilitates the quick operation of overcurrent protective devices like circuit breakers or fuses, which in turn minimizes the risk of electrical shock and equipment damage. The NEC outlines specific requirements for equipment grounding conductors, including their sizing, material, and installation methods. These requirements are detailed in Article 250 of the NEC, which is dedicated to grounding and bonding. The primary function of the EGC is to carry fault current safely. When a fault occurs, such as a short circuit between a live conductor and a metal enclosure, the EGC provides a path for the fault current to flow back to the source, which is usually the transformer. This surge of current causes the overcurrent protective device to trip, disconnecting the circuit and preventing prolonged exposure to dangerous voltage levels. The size of the equipment grounding conductor is determined based on the size of the overcurrent protective device protecting the circuit. The NEC provides tables that specify the minimum size of the EGC for different ampere ratings of overcurrent devices. For example, Table 250.122 in the NEC provides guidance on sizing EGC for various circuit ratings. The material used for equipment grounding conductors is typically copper or aluminum. Copper is a preferred choice due to its excellent conductivity and corrosion resistance. Aluminum is also used, but it must be sized larger than copper to achieve equivalent conductivity. The NEC specifies the acceptable materials for EGC and provides guidelines for their use in different environments. The installation of equipment grounding conductors must adhere to specific requirements to ensure their effectiveness. EGC must be securely connected to the metal enclosures of electrical equipment and must be run along with the circuit conductors. The NEC provides detailed instructions on how to properly install EGC in various types of wiring systems, including conduit, cable trays, and flexible metal conduits. Let's discuss the role of ground and bond testing and why it's so important in electrical systems. Ground and bond testing is a critical process used to verify the effectiveness of grounding and bonding systems in electrical installations. These tests ensure that the electrical system is safe, reliable, and compliant with relevant codes and standards such as the NEC and MSHA regulations. The primary goal of ground testing is to measure the resistance of the grounding path. A low-resistance grounding path is essential for quickly clearing fault currents, which helps prevent electrical shock and equipment damage. Ground testing involves using specialized equipment, such as ground resistance testers, to measure the resistance between various points in the grounding system. The test results are compared to acceptable limits specified in the NEC and other standards to determine if the grounding system is adequate. Bonding testing, on the other hand, focuses on verifying the continuity and integrity of bonding connections. Bonding is the process of connecting all non-current carrying metal parts of an electrical system to create a common electrical potential. This helps minimize voltage differences between different metal parts, reducing the risk of electrical shock. Bonding testing involves using continuity testers or multimeters to measure the resistance between bonded metal parts. Low resistance measurements indicate good bonding connections, while higher resistance measurements may indicate loose or corroded connections that need to be addressed. There are several types of ground and bond tests commonly performed in electrical installations. One common test is the three-point volt potential test, which is used to measure the resistance of the earth electrode system. This test involves driving two auxiliary ground rods into the earth and measuring the resistance between the earth electrode and the auxiliary rods. Another common test is the continuity test, which is used to verify the continuity of bonding connections. This test involves measuring the resistance between bonded metal parts to ensure that they are properly connected. Performing regular ground and bond testing offers numerous benefits. Firstly, it ensures the safety of personnel by verifying that the electrical system is capable of quickly clearing fault currents. Secondly, it protects equipment from damage by minimizing the risk of electrical shock and overvoltage. Thirdly, it ensures compliance with relevant codes and standards such as the NEC and MSHA regulations. To conduct ground and bond testing effectively, you need to use appropriate equipment and follow proper procedures. Ground resistance testers, continuity testers, multimeters, and clamp-on ground testers are commonly used for these tests. It's important to calibrate the test equipment regularly to ensure accurate measurements. The testing procedures should be performed by qualified personnel who are familiar with electrical safety practices and the requirements of the NEC and other relevant standards. Let's focus on the NEC requirements. The NEC, or National Electrical Code, is a comprehensive set of standards and guidelines for the safe installation of electrical wiring and equipment. It is developed and maintained by the National Fire Protection Association, or NFPA, and is widely adopted throughout the United States. The NEC covers a wide range of topics, including grounding and bonding, wiring methods, overcurrent protection, and equipment installation. The NEC is updated every 3 years to incorporate new technologies and address emerging safety concerns. Compliance with the NEC is essential for ensuring the safety and reliability of electrical systems. The NEC outlines specific requirements for grounding and bonding in Article 250. This article provides detailed instructions on how to properly ground and bond electrical systems to minimize the risk of electrical shock and equipment damage. Article 250 covers topics such as the types of grounding systems, the size of grounding conductors, and the methods for connecting grounding electrodes. The NEC also provides requirements for wiring methods, including the types of conductors, cables, and raceways that can be used in electrical installations. It specifies the ampacity of conductors, the proper methods for splicing and terminating wires, and the requirements for supporting and protecting wiring systems. The NEC also addresses overcurrent protection, which is designed to protect electrical circuits from overloads and short circuits. It specifies the types of overcurrent protective devices that can be used, such as circuit breakers and fuses, and provides guidelines for their selection and installation. The NEC also includes requirements for equipment installation, covering a wide range of electrical equipment such as motors, transformers, and lighting fixtures. It specifies the proper methods for installing and connecting equipment, and provides guidelines for ensuring their safe and reliable operation. Let's investigate MSHA regulations. MSHA, the Mine Safety and Health Administration, is the federal agency responsible for protecting the safety and health of miners in the United States. MSHA develops and enforces regulations and standards for mining operations and conducts inspections and investigations to ensure compliance. MSHA regulations cover a wide range of topics, including ventilation, roof control, and electrical safety. MSHA regulations are designed to prevent accidents and injuries in the mining industry. MSHA has specific requirements for grounding and bonding in mining environments. These requirements are designed to protect miners from electrical shock hazards and to prevent electrical fires and explosions. MSHA regulations require that all electrical equipment in mines be properly grounded and bonded to create a safe electrical system. MSHA also requires that grounding and bonding systems be regularly inspected and tested to ensure their effectiveness. MSHA regulations cover a wide range of electrical equipment used in mines, including power distribution systems, lighting systems, and mobile equipment. It specifies the types of grounding conductors, bonding jumpers, and grounding electrodes that can be used in mining environments. MSHA also requires that all electrical work in mines be performed by qualified electricians who are trained in electrical safety practices. MSHA conducts regular inspections of mining operations to ensure compliance with its regulations. Inspectors may issue citations and penalties for violations of MSHA regulations. MSHA also investigates accidents and injuries in mines to determine the causes and to identify measures that can be taken to prevent future incidents. In summary, when dealing with motor grounding in steel structures, it is essential to consider the existing bonding and grounding infrastructure. If the steel structures are adequately bonded and grounded, adding redundant grounding wires may not be necessary. Always conduct thorough ground and bond testing to verify the integrity of the grounding system and ensure compliance with NEC and MSHA regulations. This ensures a safe and reliable electrical installation. Remember to consult with qualified electricians and inspectors to ensure that all electrical work meets applicable codes and standards.